Today we'll demonstrate the advantages of the direct and indirect water-cooled resistors compared to naturally cooled resistors. The surface temperature rise and cool down times will be compared and analysed. Thomas Boudinot, our project manager, will do the demonstration. This is the direct water-cooled resistor DCRF, and here is the indirect water-cooled resistor WCR, and finally the naturally air-cooled wire-wound resistor. The same power, 1500 watts, will be applied on the DCRF, on the WCR, and on the two air-cooled wire-wound resistors. The surface temperature will be captured by infrared camera and displayed on this screen: DCRF, WCR, and one for the air-cooled wire-wounds. The water flow is set up at around 8 litres per minute and 40 degrees C for the DCRF and WCR. The coolant is a mixture of deionized water and 40% glycol. We will now apply the same power, 1500 watts, on the DCRF, on the WCR, and on both air-cooled wire-wounds. On the DCRF, the temperature increase is very limited, 5 degrees C maximum, and steady state is reached very quickly. It's the blue curve. On the WCR, the temperature increase is slightly higher, 40 degrees C maximum, and the steady state is reached after 15 seconds, the black curve. The temperature increase on the air-cooled wire-wound is slow and continuous. The steady state will be reached in terms of several minutes. The surface temperature continues to increase to surpass 250 degrees C after 300 seconds. That's the maximum our thermal camera setup can record. With 750 watts, the skin temperature will rise to 400 degrees C. Now we shut off the power. The surface temperatures of the DCRF and WCR immediately drops down, and it takes only a few seconds. For the naturally cooled resistor, more than 10 minutes are necessary for it to cool down and return to its ambient temperature. In conclusion, high-power wire-wound water-cooled resistors, the DCRF and WCR, when compared to naturally cooled devices, allow you to reduce the size of the component because you can achieve up to 10 times more power for the same size of part. Also, you can eliminate external radiation because up to 99% of the power is dissipated through the coolant. The design benefits for the user are to eliminate parasitic temperature radiation, which is an effect on other components, and also to enable you to reduce the overall size and weight of your end equipment.